Welcome to the Augmented Life podcast. Sit back and let your hosts, Lara and David, take you on an exploration of the interaction between AI technology and social systems.
Hello, Lara. Can large language models reason? This Apple paper says no, except I don't think it really says no, but that's what people on LinkedIn and the internet are saying.
It based on what I've not said to tell me my blind spot. And so it has to deductively reason that if I'm saying the world is white, you may not have considered blue or green or red or lots of other things.
Right. So how do you do that without reasoning? And
yeah,
I think a lot of people who work in the field of LLM research either don't actually use LLMs a lot for things that are not experimental, right? Just for normal, like as the conversational help agent, or they have a really specific view of human learning and human reasoning. So one great problem is if you're an AI researcher, you probably work with other people who are not typical. So reasoning in general, when you work in the social sciences, human beings don't do a ton of it. Like they tend to do, most of our decisions are made by heuristics, which are essentially associations. And so LLMs do primarily associative reasoning, which doesn't mean you're not capable of other things, although that's kind of the story in the street. I don't think it's right. But most humans use associative reasoning most of the time, right? You are just spitting out the next token, right? Which is a criticism that they make of LLMs a lot. And it's like, you haven't really done a lot of human education, have you? Like, that's what people do. They're statistical prediction engines following patterns, the patterns they observe, the patterns they're taught. And I think you really see it like if you try to teach a kid math, because math is alien. Like humans cannot intrinsically do it. And so they have to, like all the mistakes that LLMs make in math are things that you see in grade school math, right? Where people are like, so this paper, for example, talks about if you introduce irrelevant ideas into the conversation. So they'll give it a math problem as a word problem. And they'll introduce problems like while wearing socks or like just irrelevant, distractors, or while wearing 3 socks. And then that's got a number, right? But if you've done that with kids, like little kids when they're first learning math, like they're like, how do the socks factor into the problem? How can I use this number 3?
I have a great story for that. So yeah. I was teaching addition problems. Say just 2 + 2 is 4 kind of a stuff. Yeah. So I pull out the picture that is the official picture I'm supposed to use to be teaching this from my employer, and it's ducks. And I show a picture of ducks, and the question is, or the prompt is, let's make a addition problem of these ducks that are sitting and standing. And so the kids are supposed to go like 6 + 2, as in like 6 ducks are standing and 2 ducks are sitting equals 8, right? Should be all great. Except that the kids go like, that duck is having a nap and that duck is lying down. That duck looks like it's squatting. Like, I don't know which ones are sit. And then I look at the picture and I realize they're totally right. This is a very ambivalent group of ducks. It's not like, it's like they're just hanging out together. It's like a plethora, group nap of ducks. So then we start kind of going like, at what point is a duck standing or sitting? Where does it cross the line? It becomes this whole arts thing. And there are several other adults in the room, just to be clear, there's TA support, teacher's assistant. So there's full-grown adults who are also looking at this picture going like, yeah, I can't tell which ones would be considered standing and sitting.
Because we threw a simplifying assumption on it, right? And then we forgot that we threw a simplifying assumption on it. So when people look at it with fresh eyes, it's not so clear. Like what parts of the problem are relevant. And when I'm programming AI agents, one of the things you've got to get them to do as an actual explicit logical step, you've to instruct them on it, is discard the parts that seem irrelevant, right? You've got to teach that. That is not a thing that naturally just happens. Like people have magic logic, skills, and so that they discard the irrelevant information. You discard the irrelevant information because somebody taught you that was the thing that you needed to do, and then you practiced it, and then you learned it. So when I see LLMs not discarding irrelevant information, you're like, you didn't teach them to discard the irrelevant information.
But I would say that is actually where I love LLMs. Like what people would consider the deficit, I think is their greatest strength, because I put into the LLM my understanding of a situation with all of the details, all the ducks. I describe all the ducks. And then because the LLMs are not fully taught yet, thank goodness, to discard the irrelevant information, the response that I get will pick out the smallest detail of my prompt, and it will explore it and blow it up and really work it. Like, what is a sitting and a standing duck? And then that will allow me to actually reason properly. So it will take the smallest. Pardon?
You use it kind of as a reasoning partner?
Exactly. I use it as a reasoning partner because it will, like, there is confirmation bias. So I will say, okay, I've got, this thing, there's 10 different details involved, and I'm automatically picking, the 2 that I think are cognizant. But because I put in the 10, it will pull out way more information because it will actually analyze all 10 of them as if they have equal importance. And in that way, I can see the situation from all sides.
Yeah, so when we talk about association, I think in the social sciences, especially psychology, they study association-based reasoning and cognition a lot because people do it quite a lot. So the example is the stoplight problem, right? You take a stoplight and you either introduce a stoplight where there wasn't one, or you take one away where it used to be there. If you take one away where it used to be there, for the first couple of weeks, people will drive to that spot and stop. There is no stoplight, right? It's not there. But what happened is they formed a pattern of getting to work. So first, when they explore the problem, it's very difficult. There's all this complexity. And then they have to kind of really find their way through it. And then as they do that, they build a reasoning path, which is really just associations, right? It's just, I go here, I do this. I go here, I do this. I see this, I turn this, right? And then when you take part of the environment away that they don't expect, they don't reevaluate the environment all the time. Like they've built a reasoning chain based on association. So you emit the next token a lot. You stopped at the stoplight because you expected statistically the stoplight to be the next thing that was there, and it wasn't. So before we get so down on associative cognition, realize that most of human reasoning is association. Like that's how we get through our lives, because it is very energetically expensive to actually do a breadth first tree search and look at all the possibilities. It's overwhelming, all of the, the different paths and branches that you can go down. And so your brain is constantly trying to crush things down to here's an association. And even when you take things like mathematical reasoning, really, do you know how people learn to multiply? We literally give them a table and teach them just through brute force memorization. Yes, there's a theory behind it and they sort of know it. And if you think that that's just grade school elementary stuff, how did you learn to differentiate and do integral calculus? They are patterns, right? You're oh, I have x, with an exponent, I take the exponent down, I carry the x through, and differentiate. It's a pattern. It's a learned pattern. So most...
Or even if you're going to have a shower, a shower is 18 different steps and activities. Yeah. But you just, the same way LLMs go well, after the word the is usually an article, is it, whatever. It's the same thing. We're after we shampoo, we condition, and then we wash our armpits, and then we wash our feet. And it's all of these little steps that just kind of all get strung together. We're not going, what would be the best body part to wash next? Right.
You don't. You execute a pattern. Mm-hmm. And so then when you're, if you're a scientist, you are doing a lot of actual explicit reasoning. Explicit reasoning is really slow. It's actually economics, but the field of economics, Daniel Kahneman got a Nobel Prize for identifying what he calls systems 1 and systems 2. It's really psychology. It's value-based psychology, the economic part of psychology. But system 1 is just essentially your association-based reasoning. System 2 is your explicit reasoning, and it was much slower. It's over a factor of 10 slower, because you have to think through all the branches. Okay, I know this. Now, what do I know about that? Okay, what can this lead to? It can lead to this and this, this, and this. Okay, but what is it likely to? Okay, what arguments before and against each one of those branches. System 2 thinking, first off, people don't do it a lot. And second, it's not clear everyone can do it. Probably most of humanity does not really do that a lot, if at all. If you are an academic, that's the thing that you're really good at, and you spend a lot of time in System 2.
I think I live a lot in System 2.
Yeah. So let me talk about the paper a little bit more. So what do? So they take these word problems, and then they set up a framework where they can do two things. They can change the number in the word problems, and then they can introduce irrelevant other details. They can change actually three things. They can change other details. So, like, for example, they say, instead of ducks, we'll change it to geese, or we're going to change it to oranges, we're going to change it to bananas, right? Or then the irrelevant details might be things like, while I'm standing on the seashore, while 3 planes are flying over. And what they find is that all models were significantly shifted in performance worse as soon as they started changing the numbers, or introducing irrelevant details, or changing some of the words in the problem. And people have taken that to say, well, but that means LLMs aren't really reasoning. But what they'll do is take, like I say, a ChatGPT, I think 4, which was the best one they scored. For some reason, they didn't evaluate Claude, which is kind of interesting. There was a paper at Apple, very well written paper, by the way. And maybe there's some commercial thing where they're going to partner with ChatGPT and not with Anthropic or something, because it was very odd that they evaluated Google, models and Llama and Mistral, but not the other big top reasoning model for some reason. But the best one.
Who owns Claude? Can you?
Anthropic.
Anthropic does. Okay.
Yeah.
So either there's something brewing in the back.
Yeah, it was kind of a weird omission, because you're like, why didn't I mean, if I want a top reasoning model, like, my go-to models are going to be Anthropic Claude, which is my favorite. Probably Claude 3.5 Sonnet. OpenAI, the newest one, I guess probably is kind of their top model right now. And then Mistral Large is pretty good. I use Mistral Large 2. So those are kind of the top reasoning models. And it's just weird that they left one out. But what they found is that their top model they looked at was OpenAI's O1. And O1 was the least deviated as you started changing the description of the problem, but it was still significantly deviated. So their point was, all of these models are deviated, which doesn't surprise me at all. Actually, I would have expected that, but it was very surprising to most, I think, in AI practitioners. And then basically the better at reasoning the model really was, like Math Trial, which is a special mixed trial that is fine-tuned on mathematical reasoning, was much more resilient to the problem being perturbed than Mixed Trial, which is just your normal kind of just the baseline model from Mistral, which is French company.
And also, just going back to the deductive inductive reasoning, have there been studies, or in that paper did they talk about the unknown unknowns? When I evaluate a situation, usually especially behavioral, there's a specific context, and then what I'm told is what the student did, what the consequences were, basically what went down, as if it was kind of like a police report. But then my brain goes in and goes this is missing and this is missing. Where's this information? They didn't mention this part. And then that is usually where the gold lies in terms of finding the solution to the problem.
Yeah, they didn't. And they didn't, you began by breaking down the different types of reasoning because you're an educator. And so that's how you look at reasoning. They were well, there's the right way to do it and the wrong way. And you're
yeah, and that's usually the problems that are brought to me is they were supposed to do A, they did B. Fix it, make them do A. And so that's one type of reasoning, but usually that reasoning would just go to consequences. Let's change the consequences. Let's change whatever. But then I go in with a different type of reasoning, which is invisible to most people. So they think that I'm not getting what they're saying, basically, because I start asking questions like, who else was present? What happened right before that? Why did they do that? At what point did they do that? Where did it flip? And then that's usually where that's the anxiety kicked in, because they have to show their work because the whiteboards have to flip over. Let's just not have them flip the whiteboards over as a mandatory thing. Problem solved. No anxiety, no consequence, no spin-off, no blah, 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 no big problem anymore.
Yes, you have to kind of be able to reasoning back through the chain of evidence as to what happened and inform theories and test those theories. So again, when you're programming agents, it's a similar kind of thing where you have to. So I guess in prompting by itself, right? So at one point, people realized that models got significantly better when you asked them to explain their reasoning. So that's chain of thought, show your work or explain, think step by step. There's various variations of those. And it works well with people too. So once again, like all of these techniques from psychology and education can be applied to models more frequently than not. Because, and for the same reason, because you're basically an associative reasoning system. So when you have to do math, you cannot do it by just following associations. And but you'll try, and you'll see again, little kids are like, well, but ducks are different than geese. And so you gotta be like, no, there's an abstract concept in here. Like, let's talk about, like, let's just draw the same picture with ducks. Let's draw the same picture with geese. Let's draw the same picture with robots, right? And what you're trying to do is get them to understand this higher level abstract concept. You have to train them on the abstract concept. And then when you do that, it exists at a higher level, at a physical, like, association level. It's sort of like running a program inside a program. When you use a virtual environment on your workstation or something, right? It's an emulation layer. It's much slower, but you actually have to, build something that's not native to the way that you think. Humans don't natively think in math, right? So anytime you have to do math operating, that's why, for example, we all know how to do arithmetic, but we will pull out a calculator. And there was great concern that we brought in calculators to the classroom. Kids would not learn math. What happened is they do learn math, but then you still use the calculator all the time because it's energetically a lot more efficient to have some, computational device that's actually good at doing math. Do it versus when you try to do it, you have to think in abstractions. You have to do like 3 of these things, right? And 3 is not tokens. I think in tokens. I got to build abstraction and, so I have to think about the abstract operation of addition. Okay. And then I'm going to go to rules. How do I do that? I write it down. Like if you try to make people do math without paper, a lot harder for them. Because you can use the rules on paper. What's that?
Plus, you can spell out boobs.
Yes, right. With the calculator, flip it upside down. Yeah. So I guess what I got away from this paper was that it does find some very valuable things in terms of training, but there was nothing I think that an educator or a psychologist would be particularly shocked by. And people have taken it to be like, well, see, there's no reasoning, but it's this statistical parrot argument, where you're like, well, it's just following statistical associations. And it's like, that's what people do, right? You should go learn about human cognition. Go read a human cognition textbook, right? Go take, introductory psychology, like go through the cognition module of it.
A good little story about that, because I was teaching math to this little girl who was a recent immigrant. And so I had her in grade 5, but she arrived in grade 2. So at the beginning of the mathematical concepts, maybe even grade 1. And so when I got her in grade 5, everyone was sure she had like a very severe learning disability around math. And it certainly looked like that, because you would give her, 2 images or any kind of a problem, and she would just start doing random things. So it would be a multiplication. She would start adding numbers and then dividing by 2. It felt like one of those skill questions that you have to answer to enter your name in a prize. She'd be like, well, we just add these things and then we divide by 8 and then we just move this one over to the tens column, and then it was just chaos. And I couldn't figure out exactly, I couldn't find her hole. Like I kept going back and back, and I didn't even know what was happening here. And then I realized she learned math when she had just arrived. And so her brain made associations based on her extremely limited English language capacity at the time. So the teacher is teaching them how to add and then divide and subtract and multiply. And she's just kind of grasping at straws and going she's not getting
all the words, so she doesn't even understand the statement.
No, what she's doing is she's grouping associations. Okay. So she's associating. She doesn't have the words addition, subtraction, division. She just has calculate, basically. So that one word just means all of those things at one time. And so even though her vocabulary got progressively better, and then when I worked with her, she was fluent, she had learned it when she only knew 10 words. So she was just grasping at and the way that she was trying to learn was associating what she knew, which was limited, with these new concepts. And so it was association, but in chaos. And so basically I just had to hand her jump math, primary through 5, and be like, good luck this summer. Here you are. Just just go through this, and by the end, you'll be fine. You just have to teach yourself math again now that you know English. So I think that that's kind of a little bit of what sort of happens with the LLMs as well, is the association, because it can go lots of different ways. That works for English, but it doesn't work for math. You can't associate to addition if you're supposed to associate to multiplication. Like you can't, there's the extraneous details problem, but then there's the association. Their strength of being able to associate in all these different directions is a liability with math, because math is, for most of what we're using it for, is like straight lines, basically.
Yeah, and that's sort of what the paper says, is that basically the LLMs, they're trying to associate all the time, right? They're trying to turn it into a language problem, because that's really what they're good at, is emitting token streams of language. And most of what they've been trained on is language. It's not calculation. And there was Microsoft did this textbooks are all you need paper that I think moved the art a lot forward, where they said that, you could really get much higher scores by given very clean, very clear textbook-like problems. Like that you use far fewer examples if you gave it like very clear problems. And that doesn't surprise me, because what it does is it keeps you from forming irrelevant associations like your student, where they're just grouping things in that aren't the right thing to do.
I would totally agree with that. I saw yesterday, I saw a math sheet that had been like teacher created that was very simple. Take this repeating pattern and translate it into a letter repeating pattern. So it was like circle, circle, heart, star, say. Circle, circle, heart, star. So it's supposed to be A, B, C. Simple, right? And then circle the root pattern. Also simple, right? Circle, 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 heart, star. But she had gone all the way to the end of the line and then started on the second line, but only put 2 circles on the second line and then stopped. And I'm sure with the keypad, it was just like, cut and paste 4 times, and it just happened. But that meant that there was a line of pattern, and then there was 2 more icons, the second line. So do you circle the root pattern that is the first 4, or do you circle 4 circles? Which is it? Like, that is immediately not clear textbook wise.
Yeah, and it's just like if you ever tried to like match encryption keys, where you're like your signature should match this, right? You've got to cut and paste them into a clear notepad or something, so you can have one above the other. Because if they're misaligned in any way, you have a very, very difficult time. Because again, we work the same way. We're token processors, and so
Absolutely.
like when the arrangement of the tokens physically does not match, like if you take 2 different phrases, right, and you're trying to see if they're the same passphrase, you put them right on top of each other, it's very obvious, because your eye can just go up and down. If you skew them, it is very difficult, because you can't form a good clear association. Like you're taking chunks of stuff that's misaligned. Yeah.
And in this worksheet example, you used association against the student, because it went circle, circle, heart, star, circle, circle. So what's more closely associated in a person's brain? 4 circles, similar, right? Or 2 the same and then 2 different ones. If they're saying circle, what is the, circle the things that are alike, you're kind of leading them to circle the 4 circles, unless you've explicitly taught it's solid, like.
And as soon as you wrap the line, it creates a different group, right? Now it's like, I can see a circle, 2 circles, like above 2 other circles, and like that seems
circle
to go.
That. Yep. Yeah, exactly.
Yeah, exactly.
And especially if you give that to somebody with limited language, maybe they just pick out the word circle, not root pattern, root texture, whatever. It just said circle something, something, something. They'll be like, I see circles. Yeah. Like, they could read the circle as a noun, not a verb.
Yeah, so that's the thing. It's like, well, LLMs aren't really doing, reasoning. Reasoning is a complex topic that takes a lot of effort to teach, right? And talk to somebody who teaches reasoning, and they will, they'll lay out the complexity of it. It's much more complex than people think. It's all, especially if you're an association-based agent trying to reason, you got to make sure that you prune all of the wrong associations, that you get good, clear data. And even so, like, they're like, but even if I, you changed the words and things like that, and it would skew back away from the right result into lower quality results. Yeah, but like, if you take, a model that gets 90% on these math questions, and you mix up the words in them, right? Or change the numbers, and it goes back to like 70%. On the one hand, that indicates that you're maybe memorizing answers, or it's trying to substitute answers for things it already knows, right? Yes,
maybe.
that's true.
And maybe the similar to that math, like, it's a grade 2 worksheet. Maybe you've got 75% of the kids that aren't reasoning, that are going, circle the first 4. I know that when I am asked that question, I know I have to circle the first 4 things, because that's
right.
the
repeating the wrong pattern, right?
But the smart kids, or the neurodivergent kids, or the kids that reason differently, they're reasoning circle noun, circle verb, let's circle the circles. Or they're saying, okay, well, there's this line, but then there's only 2 on the next line. So maybe I'm supposed to circle the first 4, because that's the only part that actually repeats. The circles are repeating down, really. Like the first 2, and then there's 2 more on the bottom. So it could reason down. And then
right. So the takeaway is you've got to be very precise about what you ask. You've got to be very precise about how you grade, and you've got to be very precise about the clarifying answer as to, this is why this is not right. This is what I wanted, and here's why. And if your instruction materials are not clear, the agent by default is going to learn, it's going to rely on associations, it's going to learn all of these associations that are not the associations you want it to. However, and here's the killer for the paper, when people are like, see, that proves LLMs don't reason. It's still got 80%, right? What you showed is that there's a bunch of bad associations in there. If it couldn't reason at all, it'd get 0%. It would just be, it would be like your student who's just like throwing out random stuff, just following random associations, which again, we don't have to go to LLMs for that. We can find human examples.
Well, that's the thing.
She's going to get 0.
If it's being trained on humanity,
yeah,
we all really, like, if you take all of us and we all take a test, like, the first standard deviation, like 80% is good. Like it's taking the best of us. I don't know, what
and we
the
use techniques to make it better, right? That's the other thing, is like, there's a distribution of models, so you can see these ones are trained using techniques that work better. So I'm like, no, don't give up on the LLMs can't reason. They have all the same cognitive problems in reasoning the human children have. That's not particularly surprising. And this gets back to our take on why we should be using more social sciences and AI, is that we have solutions to all this problem, right? Like, we deal with the human children every day that make all the same errors. And so anytime you develop a test like this, I'm like, you should give it to people too, right? You should get a baseline off humans.
That's my point, is that they're taking that 80% as proof that they can't. I would take the 80% as proof that they do. Because if you took all the humans and you gave them that same test and you averaged it out and you graded all the papers, you'd also get an 80% based on our neurodivergence. So I would say that, just case in point, 80% means that they reason as well as all of us would if you mushed us all together, which is kind of what an LLM is. All the brains mushed together.
An average across the human population.
We would not score 100. We just wouldn't. We would not.
The takeaway from this is that, like, when you find a good AI paper result, try it on people too. And obviously there's a social science literature behind it, and you could probably go find out what people do, which is even better. But even just like simply baseline against people, right? And see, because if your argument is that LLMs can't reason, the same argument can then be applied to people. Like, well, people can't reason, because if you see the same shift in the human population, which you will, right?
Yeah. Or you just pull any random elementary school teacher and be like, how would your classroom do? They'd be like, meh, about half of them would get it, depending on the student population. And then you'd have a couple that do this and a couple do that.
Exactly.
Oh, that's what we found as well.
Final word, like, teaching is a skill, right? There's an entire field, there's an entire body of literature and research around it. There's an entire body of skilled practitioners who do it. And this gets back to our elephant in the room article, right? You should put a teacher on that team, and they will tell you things like, oh yeah, you're going to see that, and this is why. And it doesn't mean that they can't reason. It means that you've allowed them to form incorrect associations, and that's going to degrade their reasoning.
And also, maybe it's like a Darvo switch, a victim offender switch, and you've actually given them basically a picture of a bunch of ducks that are, some are squatting and some are standing and some are leaning slightly to the left. So it might actually be a problem with the test.
Right.
Did you line up a bunch of circles or not? Like, was that a clear question?
In fact, we saw that on one of the big LLM tests. I'm trying to remember which one it was, but one of the major tests, and Philip from AI Explained has been going on a lot about this and the errors in the test. The MMLU, I think, yes, that was it. Like a certain percentage of the test questions, I think it was 3 to 5% were just wrong. Were wrong. That you trained it on wrong answers, right? So you trained it on, you used it to evaluate performance, and the actual questions that you're using for evaluation are wrong. So, it's just minimization of error, but there's a lot of errors that can be made. And we tend to restrict ourselves to only saying a reasoning entity should do this, or could do this or that or the other. Talk to an elementary school teacher and you will find all of the mistakes that cognitive entities, we all agree they're cognitive, and nobody's arguing that people can't reason, even though most people don't reason most of the time. You can teach people to reason. It is not easy, and there's lots of room for mistakes in the data, mistakes in the questions, and mistakes in how the associations are formed as you teach them.
Any clinical test, it goes through thousands of iterations. They're all about 10 years old because they just look at the test question. How many people got it wrong? Of the people that got it wrong, is that an error with the test? Is that leading them astray? And then you revise your questions over and over. Every professor looks at their exam, revises the questions to make them less unclear so that it's more statistically significant of the actual students learning. That's what happens. I feel like a lot of these tests, they just kind of wrote them and gave them and they're like, that's done. But actual good tests, they revise these things for decades. Decades.
Yep, definitely. All right, so I guess let's wrap up with the summation that it doesn't mean it's a good piece. It's a good paper, right? It's well written. Yeah. It's very helpful result. It'll help us train LLMs better. I don't think it's unexpected to people who work in education, especially. And I guess the big takeaway is it does not mean that the agents can't reason. It means that models can easily be distracted and that we need to figure out how to train them better.
AKA, it means that models reason like we do.
Exactly. All right. Catch you next week.